Today we are going to continue our conversation about power series solutions. So let's remember from last class, it was last class, we talked about the difference between a regular solution and a singular, regular point and a singular point. No, ordinary point. Sorry. We talked about the difference between an ordinary point and a singular point. So remember that an ordinary point was one where the coefficient functions were analytic at that point. Okay, and mostly we did zero, right? All the solutions we've done so far have been at zero. So zero is an ordinary point if the coefficient functions were analytic at zero, meaning we could find a power series representation of the function at zero. And if we could not, meaning usually that means that the function was undefined at zero, we call that a singular point. Well, today, so for the most part, we want to have our power series solution centered at zero. If zero is an ordinary point, we talked about how to do that last class. Today we're going to talk about what if zero is a singular point, meaning what if one of the coefficient functions is undefined at zero? Well, in certain circumstances, we can actually find a series solution centered at that singular point. So x naught is a singular point if p of x or q of x is not analytic at x naught. Again, means p of x or q of x, or maybe both, are not nice at x naught. So usually this means dividing by zero. Okay, so if notice the lead coefficient is 1. If it's not, we would divide by that lead coefficient, and so p of x and q of x might be a fraction. And so if we have to divide by some value of x in that fraction, or plug in the value of x to make us divide by zero, we call that a singular point. Well, a singular point x naught is called a regular singular point if x naught is a root at most once in the denominator of p and at most twice in the denominator of q. What that means is a regular singular point is a value of x that you'd plug in, and the result is dividing by zero, but only a little bit. And I realize how ridiculous that sounds. I'll show you what I mean by that. Let's consider this problem here. X squared minus 4 quantity squared, y double prime, or whatever. You can read the problem. So to identify singular points, by the way, there are no directions on this problem. We are going to do two things. We're going to identify all of the singular points, and then we're going to classify them as either regular or irregular. Now to do that, first thing we need to do is divide by that lead coefficient. So I'm going to divide each term here by that x squared minus 4 squared. And so that becomes y double prime plus 3 times x minus 2 y double prime over, y prime there. I'm going to simplify the bottom. Notice that x squared minus 4 factors as x plus 2 times x minus 2. So I'm going to do it that way. I'm going to do x minus 2 squared, and x plus 2 is also squared. And the advantage of doing that, of course, is one, in that middle term we have a little reduction. So y double prime plus 3 over x minus 2 times x plus 2 squared times y prime plus 5 over x minus 2 squared times x plus 2 squared, y equals 0. Okay, now hopefully you guys will agree that the values of x that make us divide by 0 would be x equals 2 and x equals negative 2. Both of these are singular points. Now, x equals 2 is what's called a regular singular point. And it's regular because, so the x equals 2 is singular because both of the denominators have a factor of x minus 2. Notice that factor appears only once at the bottom of y prime and only twice in the bottom of only once in the bottom of p of x and only twice in the bottom of q of x. And that's what we call regular. X equals negative 2 comes from the factor of x plus 2. Notice that q of x is fine, right? We're dividing by that factor twice. Q is not a big deal. In p, we're dividing by the factor more than just once. So for that reason, negative 2 is an irregular singular point. So that's what we're talking about here. So again, both of them make us divide by 0, but x equals 2 only makes us divide by 0 a little bit. And yes, again, totally ridiculous, whatever. So the point is, it is actually able, that's not what I meant to say at all. It is actually possible for us to find a series solution centered at a regular singular point. And that's our goal for today, is to figure that out. And by the way, in this example, our singular points were 2 and negative 2. Again, for this class, we're pretty much just going to always center at 0. So the question is simply, is 0 a regular singular point? Well, to find that series solution, we're going to use what's called Frobenius' theorem, which right away is probably the most fun word we're going to get to say in this class. So I encourage you at home, say the word for me, Frobenius. It's just fun. Now, if x naught is a regular singular point, then there exists at least one solution of the form, of this form here. Now, what I want to point out is that this is that power series centered at x naught that we've been working with so far. And by the way, for our purpose, again, generally we're centered at 0. So this would all be written as x to the r times the sum n equals 0 to infinity times cn x to the n. This is what it looks like if our if our x naught is 0. Notice that this whole thing right here is that same power series that we were working with all of last class and a little bit the class before that. The only difference is now, because 0 is a regular singular point, we're going to take that power series and we're going to multiply it by x to the r. Keep in mind that r can be any constant. R could be positive or negative. R could be a whole number or a fraction. R could be 0. I mean, R could be anything. Anyway, and then to get to the second form there, basically we're going to take that x to the r and bring it inside. And so it combines with that x to the nth power. So it'd be cn x to the n plus r. So when we were centered at an ordinary point, this was last class, we assumed that our solution was just a nice plain old normal power series. If we are centered at a regular singular point, we are going to assume that our solution is that power series multiplied by x raised to the r power. Okay, this is called the method of Frobenius, which again, fun to say. It's worth pointing out that the solution is an infinite series, but it may not be a power series. Remember that a power series is an infinite polynomial. A power series is adding terms that are powers of x raised to integer powers. Actually, not even integers, whole number powers, right? Negative powers don't even work. Please notice that we are assuming that we're taking that power series that we've been working with and multiplying it by x to the r power. If r is a negative number, now suddenly our terms might have negative powers on x. If r is a fraction, now suddenly all of our x's have fractional powers, which is fine. I mean, that's not a big deal. It's still it's still an infinite series. It's still it's the answer we're looking for. Just understand that we wouldn't call that a power series because the power series is specific. It is just whole number powers of x. And here we're not assuming that our x's have whole number powers. Again, not a big deal. It's not going to affect our work any. It's just that the phrase power series would not apply. All right, so let's check out this example. And let's just really briefly verify. By the way, I should mention again, we're only going to have solutions centered at 0. And furthermore, the directions for this problem would say, find the series solution centered at the regular singular point x equals 0. So it'll be crystal clear that it might even say use the method of Frobenius. It'll be crystal clear that that is what you're going to be doing for this problem. But again, just to verify that it's a series solution, that it's a regular singular point, let's divide everything by that lead coefficient of 3x. I'm going to erase this in a minute because we don't need to do this, but just for our own purposes here. Okay, so notice that x equals 0, certainly we're dividing by 0 in both terms in this case. Doesn't have to be both, one is plenty. Notice that that factor of x appears at most once in the bottom of P and at most twice in the bottom of Q. I say at most because if it's only once, that's fine. If it doesn't appear at all in the bottom of Q, that's also perfectly fine. X equals 0 is a regular singular point. Now, I want to make sure that we're clear that the only time you ever need to divide by the lead coefficient is to verify that it is a regular singular point, or to identify ordinary or regular points. When you're actually solving a differential equation, we want that 3x to be right where it is. We don't want fractions because fractions are going to mess stuff up. So we are completely happy with that 3x being right where it is. Now, what is it we're assuming? We're assuming that y is equal to the sum n equals 0 to infinity of Cn x to the n plus r. We're making a different assumption than we did last class. Now, we're going to have to take this and plug it into my equation, so I also need y prime. Y prime, let's take the derivative, is the sum. I'm going to talk about the n in a minute. It's Cn times n plus r, x to the n plus r minus 1. Now, unlike the method we used last class, the n is going to continue starting at 0. That is not going to change. It is still going to start at 0. Because remember, last time when we took the derivative, it was n times whatever. When n is equal to 0, that term goes away. Let me put it a different way. When n was 0, that was our constant, and when we take the derivative, the constant goes away. But now, that constant is multiplied by x to the r power. So when we take the derivative, it's still gonna be there. So notice for this method of Frobenius, the index does not change. When we take derivatives, n continues to start at 0. Y double prime is going to be the sum n equals, again, 0 to infinity, Cn times n plus r, n plus r minus 1, x to the n plus r minus 2. Okay, let's plug those in. And so we're going to get 3x times the sum n equals 0 to infinity of Cn times n plus r, n plus r minus 1, x to the n plus r minus 2, plus y prime minus y equals 0. Let's bring in the 3x. So we get the sum n equals 0 to infinity of, I'll leave the 3 in front, so 3Cn times n plus r, n plus r minus 1. Now it's going to be x to the n plus r minus 1 power, plus the sum n equals 0 to infinity, Cn n plus r, x to the n plus r minus 1, minus the sum n equals 0 to infinity, Cn x to the n plus r equals 0. Okay, let's take a step back for a second. Our goal is the same as the goal from last class, to find those C's. Find C0, C1, C2, da, 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 da. Our goal is the same. Our method is going to be the same. I'm going to start by making it so that all the x's are raised to the same power. And I'm going to do that by changing the index. But when I change the index, I'm only going to use, so my new index is k like last time. I'm only going to use k's and n's. The r doesn't go anywhere. What I mean is, once I've changed the index, these are all going to say not x to the k, but x to the k plus r power. I can change the n's into k's, but that r is not going to go anywhere. N is the index, but r is a constant that's actually going to be part of my final answer. So notice in the last summation here, n equals k, that's fine. In the second, and actually both of the other two, notice that I need that n minus 1 to become a k. So n is equal to k plus 1. So I need this to say x to the k plus r, which means that n minus 1 has to turn into a k. And in fact, the same is true for the first term as well. So likewise, I'm going to let k equal n minus 1. So n is equal to k plus 1. Okay, change the index like we did before. Sum. So now notice that when n is 0, k is negative 1. So k equals negative 1 to infinity of 3 ck plus 1 times k plus r plus 1 times k plus r, x to the k plus r, plus the sum, again, when n is 0, k is negative 1. We get ck plus 1 times k plus r plus 1, x to the k plus r. And then the last one here, minus the sum, k equals 0 to infinity, ck x to the k plus r. That was just the direct substitution. Okay, we've now made them so that all the x's are to the same power, right? Great. Next thing we had to do was take out the earlier terms so that they all start at the same k. So notice I need to take out, in the first term, I need to take out the term where k is negative 1. So for that first term where k is negative 1, that's going to say 3c0 times, when k is negative 1, it'll be r times r minus 1, x to the r minus 1 power. I'm replacing all the k's with negative 1. The second term, again, plug in negative 1 for k, I get c0 times r, x to the r minus 1 power. Okay, now all the terms start with k equals 0. All the series start with k equals 0. So now I can put them all together, and again, just like last time, grouping them all. Each term is x to the k plus r, so I'm going to factor that out. And the coefficients are 3 ck plus 1 times k plus r plus 1, k plus r, plus ck plus 1 times x plus r plus, or k plus r plus 1, minus ck, and that whole coefficient is multiplied by x to the k plus r, and all that's 0. Okay. Let's look on the left side, the first two terms there. Notice that both, these are like terms. Now remember, when we talk about like terms, we mean terms that have this x raised to the same power. These both have x raised to the r minus 1 power. So I can combine the coefficients. When I combine those like terms, the coefficient will be 3c0 times r minus 1, plus c0 times r. And that's going to be, so that's the coefficient for x to the r minus 1. And that's equal to the corresponding coefficient on the right side of the equation, which is just 0, because they're all zeros. Let me factor this out. We can factor out a c0 and an r. And we're left with 3 times r minus 1 plus 1. So, first of all, c0 can't be 0. And I'll maybe we'll get to that at some point, but basically C0 can't be 0. So when I solve this, I'm just solving R times 3R minus 2 equals 0. I'm getting R equals 0 and R equals 2/3. Now, again, let's take a step back for a second. Last class, we got two solutions, right? We always want two solutions. It's a second order differential equation. Last class, we got two solutions. And the two solutions came from two coefficients, C0 and C1, where we got to pick whatever they were. Okay, and in one method, we picked a number. Another method, we just left the terms with C0s or C1s. That's where our two solutions came from. For this method, our two solutions are going to come from our two R values. So one of my solutions is going to come from when R is 0. My second solution will come from when R is equal to 2/3. So that's, again, while this method and last class are very similar, a lot of our steps are the same, there's some very important differences, and that's one of them. Now, if I set this whole coefficient equal to 0, as we did last class, let's solve for the bigger subscript for C's. In this case, we're going to solve for CK plus 1. So I'm going to, let's see, first of all, I'm going to move that CK to the right side. And on the left side, I can factor out that CK plus 1. I can actually also factor out K plus R plus 1. And I'm left with 3 times K plus R, so 3K plus 3R. And in that second term, I'm taking everything out, so just plus 1. So what I'm finding is that CK plus 1 is equal to 1 over K plus R plus 1 times 3K plus 3R plus 1 times CK. Okay, obviously I'm going to need another slide to continue. So we have our relationships here, and now it's up to us to find our solutions. So at the top here, let me just rewrite that. CK plus 1 is equal to 1 over K plus R plus 1 times 3K plus 3R plus 1 times CK. And then again, we're going to get two solutions. One of my solutions comes from R equals 0. And one of my solutions comes from R equals 2/3. Well, we're going to do the same thing we did before. We need to find a relation. Right, maybe I shouldn't say that at this point. Let's take that R equals 0 and let's just plug it into that relation and see what it turns into. So when R is equal to 0, we get CK plus 1 equals, again, I'm replacing all the R's with zeros. So I'm getting K plus 1 times 3K plus 1 times CK. Now, here is where, like I said a second ago, this is where I'm going to do a little bit like I did last time. I'm going to let C0 be whatever it wants to be. In fact, let's make it even simpler. C0 is just going to be a 1. Okay, I'm just going to leave it as a 1. And now let's find C1. Now notice to find C1, that's going to happen when K is 0. So if I plug in 0, C1 is equal to 1 over 1 times 1 times C1, and times C0, and those are all just 1s. When K is equal to 1, this tells me the C2 is equal to, so we get 1 over 2 times 4 times C1. So this is going to be 1/8. Okay, now again, I need 3 non-zero terms, and there are the first 3 non-zero terms, so I can stop because I got 3 coefficients that are non-zero. Okay, here we go. My first solution is C0 plus C1x plus C2x squared plus ... But remember, we made a different assumption at the beginning of this problem. We assumed that our solution wasn't this big power series. It was that big power series times x to the r power. Well, for this solution, r is 0. So, okay, fine, that does nothing in this example. But don't forget, if you're using the method of Frobenius, your final answer is not that same power series we did before. The solution is that power series times x to the r power. But here's my first solution. For my second solution, again, let's assume that C0 is 1. That's fine. Oh, I'm sorry. First, I need to figure out what my relationship is here. So now I'm going to plug in r equals 2/3. So I get ck plus 1 is equal to 1 over k plus, well, 2/3 plus 1 would be 5/3. And then 3k plus, well, let's see, 3 times r would be 2, plus 1 more is 3 times ck. Okay, now, I'm going to be a little sneaky about this because, okay, fine, fractions suck. I'm not going to deny it. Fractions are not very fun. Why don't we factor the 3 out of this term and then distribute it to this term? So I'm going to factor the 3 out of this term so that that second term becomes k plus 1. And then when I distribute it to the first term, it becomes 3k plus 5. And then all that times ck. So again, being a little sneaky and in the process, make the fractions go away, which is, optimal. All right, so again, now we have to find our coefficients. So C0 is 1. When I plug in k equals 0, this tells me that C1 is equal to 1 over 5 times 1 times C1, or C0, I did it again, times C0. So this would be 1/5. When k is equal to 1, we get that C2 is equal to 1 over 8 times 2 times C1. And let's see, 16 times 5 is 80, so we get 1 over 80. So my second solution is, so again, it's C0 plus C1x plus C2x squared plus dot, dot, dot. But one more time, this is not my solution. My solution is all that times x to the r power, and this time r is 2/3. So this is really our first example where we're getting a solution that looks completely different than solutions we've seen before. Because of course, if we were to distribute that x to the 2/3 power, now suddenly each term has a power that's fractional, which is fine. It's just not a power series. That's okay. Okay. So we're done with this example. We found our two series solutions centered at the regular singular point x equals 0. Awesome. Okay. Let's try. Well, let's take a step back for a second. When we solved this problem, we ended up solving this equation for r, and this is called the indical equation. And those two values of r that we found are called the indical roots. That's just what we call them. Now, the question becomes, is it possible? Let's say we didn't have to solve the whole problem. Let's say I gave you a differential equation, and I asked you to just find the indical roots, and don't do all the other work to actually solve the equation. Here's how we're going to do it. Remember how we said that p of x only has x at most once in the bottom of p and at most twice in the bottom of q. Well, if x is there at most once in the bottom of p, doesn't that mean that multiplying p by x, now suddenly there's no more x's on the bottom? And likewise, if x is at the bottom of q at most twice, that means x squared times q. Now there's no more x's on the bottom. And so that means that these new functions, x p of x and x squared q of x, neither of them have zeros on the bottom of the fractions. And so they're both analytic, which means both of them can be written as a power series. X times p of x is some power series, x squared times q of x is some power series. And it turns out that the indical equation will be this one. It'll be r times r minus 1 plus A naught R plus B naught. Again, A naught is the constant term of the power series for x p of x. B naught is the constant term for the power series of x squared q of x. Okay, so let's say, again, the directions don't tell me to solve it. They just tell me to find the indical roots. Okay, so this is really when we want to find the integral roots, when we want to find p of x and q of x. This is really the only time where we actually want to divide by that 2x. So if I simplify this, this will be y double prime plus 1 plus x over 2x times y prime plus 1 over 2x times y equals 0. Okay, this is my p of x, and this is my q of x, which tells me that x times p of x would be would be 1 plus x over 2, right? Because the x on the bottom cancels, which is the same as 1/2 plus 1/2 x. And then x squared times q of x would be x over 2, right? Because take 1 over 2x, multiply by x squared. And I could split that up, but this becomes 0 plus 1/2 x. Normally, of course, we wouldn't write the 0, but here's why we did that. This constant term is the a naught in my integral equation, and the 0 is my b naught. So that my integral equation becomes r times r minus 1 plus 1/2 r plus 0 equals 0. I'm using the a naught and the b naught. If I simplify this a little bit, I get r squared minus 1/2 r equals 0. Factor out the r. And I find that my integral roots are r equals 0 and r equals 1/2. There we go. Okay. If the problem says nothing more than find the integral roots, this is a way easier way to answer the question, because we don't have to go through any of that nonsense. We don't have to do summation, none of that stuff. We don't have to go through any of that nonsense. But of course, if the directions said find the integral roots and then solve the equation, we don't need to mess around with this stuff unless you want to check your work, because we're going to come up with those integral roots in the process of solving the equation. So you don't need to do this you don't need to use this equation unless that's the only thing you had to find. If you're solving the equation, just solve the equation. You'll find the integral roots along the way. Okay, let's try another one here. Let's solve this differential equation. X times y double prime plus y equals 0. Now, and again, the directions for this would say find the first 3 terms of 2 series solutions centered at the regular singular point x equals 0. Again, it's going to spell it all out. It's regular singular point. It'll probably be even say use the method of Frobenius. There's no mystery what to do here. Or I guess I should say there's no mystery of whether you should use today's method or last class's method. The directions will say in the problem. In fact, the last class, the directions would say find the power series solutions centered at the ordinary singular point. In fact, I think that's what the homework did. Again, spells it out for you which method to use. Okay, so let's substitute in the power series for y double prime. So that was the sum n equals 0 to infinity of Cn times n plus r minus 1, x to the n plus r minus 2, plus the sum n equals 0 to infinity of Cn x to the n plus r equals 0. Okay, using the same power series, or again, I shouldn't say power series, using the same infinite series that we used on the earlier example. Bring in the x, so this becomes the sum n equals 0 to infinity. Cn times n plus r, n plus r minus 1, x to the n plus r minus 1, plus the sum n equals 0 to infinity of Cn x to the n plus r equals 0. Okay, next up, change the index so that they both say x to the k plus r. So here just k becomes n. Over here, k becomes n minus 1. So n is equal to k plus 1. We get the sum. When n is 0, k is negative 1. So negative 1 to infinity. ck plus 1, k plus r plus 1, k plus r, x to the k plus r, plus the sum k equals 0 to infinity, ck x to the k plus r equals 0. Great. Next up, let's pull out that early term. Notice we just have to take out the term in the first summation where k is negative 1. When k is negative 1, we get c0 times r minus 1, x to the r minus 1. And by taking out just that one term, now both the summations start at 0. And so we're left with ck plus 1 times k plus r plus 1, k plus r. Okay, there's the coefficient for the first term, and then plus another ck, and all of that is multiplied by x to the k plus r equals 0. Going back to that first term, if I set that coefficient equal to 0, again, C0 can't be 0. And I think I mentioned earlier, I would explain why. Notice that in this method, each term, each coefficient, turned out to be a multiple of the coefficient before it, which means if C0 was 0, then C1 would be 0, C2 would be 0, C3 would be 0. That would be a fairly boring solution. So we can't assume that we can assume that C0 is non-zero. So if I set this equals 0, either r is 0 or r is 1. And so we end up with our two indical roots, and we end up with our, that'll lead us to our two solutions. If I set this all equal to 0, I'm going to end up getting ck plus 1 is equal to 1 over k plus r plus 1 times k plus r, x to the, or not x to the, I'm sorry, times ck. Sorry, small technical problems, but we end up getting ck plus 1 equals 1 over k plus r plus 1 times k plus r, all times ck. Okay. Okay, let's move to the next slide here. And so when r is equal to 0, let me rewrite that real quick. ck plus 1 equals 1 over k plus r plus 1 times k plus r. Times ck. And actually, I take it back. I'm going to do the other one first. I'm going to do r equals 1 first. Okay, so I'm going to do r equals 1 first. So when r is equal to 1, this becomes ck plus 1 equals 1 over k plus 1 times k times ck. Okay, once again, I'm going to start by assuming that C0 is 1. That's fine. And so to find C1, I'm going to plug in k equals 0. And so when k is equal to 0, this becomes 1 I'm sorry, I plugged in the wrong number. Hold on. Sorry, I did what I said I wasn't going to do. So I'm plugging r equals 1, so this becomes k plus 2 times k plus 1. Okay, that's better. Okay, so when I plug in 0, we get 1 over 2 times 1 times C0, so that'd be 1/2. And then when k is equal to 1, plug that in, we get C2 would be 1 over 3 times 2 times C1. So 1/6 times 1/2 would be 1/12. So we're getting that y1 is equal to, okay. So again, it's c0 plus c1x plus c2x squared plus dot, dot, dot. And all of that is multiplied by x to the r power. So here would be x to the first power. Great. Okay, so there's my first solution. For my second solution, we're going to use r equals 0. My relationship here becomes ck plus 1 equals 1 over k plus 1 times k times ck. Now, here's what's going to happen. Let's say I start with c0 equals 1 like I've been doing. Notice that in that case, to find c1, I would have to plug in k equals 0. And of course, I can't plug in k equals 0 because that would make me divide by 0. This is not going to work out. So I'm going to not start at c0, but instead I'm going to start at c1. I'm going to c1 equal 1, and we're just going to ignore the c0. So now, to find c2, we're going to have to plug in k equals 1. And so c2 is equal to 1 over 2 times 1 times c1, which would be 1/2. When k is equal to 2, we're going to get c3 equals 1 over 3 times 2 times c2, which is 1/12. Okay, so my second solution is going to be, now again, c0 is gone, which means that there's no constant term for my solution. That's okay. That's fine. That's just how we're going to deal with it, because otherwise we'd be dividing by 0, and we try to avoid that whenever we can. C1 is still multiplied by x. So it's still going to be 1 times x plus 1/2 x squared, right? C2x squared plus C3 x cubed, right? They're still multiplying the same powers of x plus dot, dot, dot. Okay, and then again, don't forget, today everything is multiplied by x to the r power. Here would be x to the 0 power. Okay, so we end up getting our second solution. Or do we? I want to point out that if I were to simplify this, then my y1, if I distributed that x, notice I would get x plus 1/2 x squared plus 1/12 x cubed plus dot, dot, dot. And my y2, if I just basically said, oh, x to the 0 is 1, I get x plus 1/2 x squared plus 1/12 x cubed plus dot, dot, dot. Okay? I'm getting the same solution both times, which is fine. I mean, it's not optimal, right? It's a second order differential equation. I want to find two solutions, and we'll address that in just a minute. But I want to remind you that Frobenius' theorem said that we're guaranteed there is at least one solution that's in this form. We only got one solution. Darn. Okay, that's fine. That's okay. We ended up getting one solution. So before we do anything else, let's ask, why did we end up getting one solution? Or maybe could we have figured out earlier in the process that we were only going to get one solution? Well, the values of R determine our solutions. If the difference between them is not an integer, the first example is a good one, when R was 0 and 2/3. If the difference is not an integer, we're guaranteed we're going to get two solutions from Frobenius. Right off the bat, we're going to get two solutions. If the difference is an integer, or if they're the same, right, we end up getting two of the same integral roots. By the way, if we get the same integral roots twice, of course it's going to give us the same solution because we're just using the same R twice. That'd be silly. But even if the difference is an integer, we might still get two solutions. We should still go through the process. But notice that last example, the difference between the integral roots was a 1. It was an integer. We still should go through the process. We just need to be aware that okay, this might end up giving me the same answer twice, and that's okay. So now again, the question becomes, how do we figure out the second solution? This is a second order equation. We need two solutions. Well, let's think back a couple chapters. If I gave you one solution to an equation, how would you find that second solution? And the answer is reduction of order. If you want to find a second solution, you would use reduction of order. And just to remind you what reduction of order is, because it's been a while, if we have an equation y double prime plus p of x times y prime plus q of x times y equals 0, and if we have one solution y1, my second solution is going to be y1 times the integral e to the negative integral p of x dx over y1 squared dx. That was our formula for reduction of order. So, for our problem, my first solution is, it was x plus 1/2 x squared plus 1/12 x cubed plus ... And let's also notice that my p of x for this problem is 0. Certainly, if there had been a y prime term, we'd have to divide it by that x, right? To talk about p of x and q of x, we need a lead coefficient of 1, but in this case it's 0, so who cares? So my second solution is going to be y1, which is that power series. And in this case, it is a power series, right? The powers of x are integers, or are whole numbers. Integral e to the negative integral of p of x, which was 0, over y1 squared dx. Oh, boy. First of all, hopefully you will agree this integral is just 1, or constant, I guess. E to any constant is just a new constant. If you were just to assume that the top of this fraction is just a 1, that's okay. Because remember, if at some point I need to write a general solution, my y2 is going to be multiplied by a constant anyway. So who cares if there's an extra constant? I'm just going to write a 1. But what we do need to do is FOIL that out, because it's squared. Then do this division, which is not a fun process. Then integrate each of those term by term. And by the way, each step of the way, we're creating a new power series. And then FOIL this out. Okay, yeah, this is never going to happen. It's not going to come up. I am not going to ask you to do this. No way. I just want to show you that that's how we would complete this problem if we had to. Anyway, that is the method of Frobenius. I figured I'd say it one more time because it is so much fun to say. That is the end of the lesson. Thank you very much for watching.